Hello. So, at some point, I had started to explore patterns with the number 9. And then I was like, well, it's interesting that we have 9 numbers, 10 numbers, that fall into the ones place. So we have 10 digits, right? They go from 0 to 9. And then I was like, well, what if we change that total? And I started doing it with 12. I was like, okay, whatever. I am just going to make up 2 symbols and add them over here. So then the number system is going to have a total of, I was like, 12 numbers. But then I'm like, but wait, it's not a total of 12 numbers. It's still a total of 10 because I moved the 10 over here. So in my new number system, it's still 10. I don't know what sounds these two make, but we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then whatever this is. We could call it AB if we want. And then it would be 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 18, B-teen. I don't know. Anyway, I was like, okay. And I was noticing that the same sort of symmetries arose. So like in our regular number system, once we get down to 5, when we're multiplying everything by 9, so like 1 times 9, 2 times 9, 3 times 9, 4 times 9, once we get past 5, it starts reversing and flipping. So like 45 becomes 54, 36 becomes 63, 27 becomes 72. And I was finding that it would like move down a row every time I skipped a column. And I was like noticing the same exact pattern happening over here. And I think all that's really cool. And now I'm like, okay, what if I just try this with less numbers rather than more and see what happens? Yeah, that's kind of where I'm at right now. So, is this gonna work? So let's pretend. If we just have the number 0, we just have the number 0. I don't know what we can do with that. Let's see if we have, I feel like I kind of want to start with 3, but I want to know what happens with 2. So I'm just going to start with 2. So if we have 0 and 1, then we have 2 numbers. Then we can make these numbers and these numbers, and is that it? So in the ones place, we would have just the 0 and the 1. Right, and so, okay. And then we could add this, or this, or we could have this, and we could have this. I don't get it. What am I doing? If we have only 2 numbers, oh, then that's how the numbers go in order. We're going to have 0 and then 1. And then we can have this number, and then we can have this number. and then we can have this number, and then we can have this number and this number. And it seems like it would increase, wouldn't it? Because each time I would be able to add a digit to the next place up. So like in the ones place, we can have either a 0 or 1. In the tens place, we can have we can have a 0 or 1. So this counts as 0 and this counts as 1. In the hundredths place, we can have a 0 or a 1. And each time we add a new place, we double. Like we went from 2 to 4 to 8 numbers. So then we'd have 16 after that. I guess that makes sense. I don't know if it makes sense for me to actually be doing this with just 2 numbers. Okay, I don't get what I'm doing. I'm going to 3 numbers for now. And then we'll see. So if we have 0, 1, and 2. So then the first number is technically 1. So we have 0 and we would follow the pattern. So we'd have 0, 1, and then 2, and then backwards we would write 2, 1, and then 0. And then I'm so confused. And then we'd have 2 and 2, because that's the last number here. But then we'd still be writing this in the same order. So we'd have 2, 1, 0, but then I'd have a 2 here, and then I'd have a 0 and a 1. But then here we'd need to add an actual number as well. So we'd have a 0, a 1, and a 2. This made more sense when I added numbers than when I took numbers away. I mean, like, the pattern still works. Maybe? Does it work if we have less numbers? Oh, I don't get it. I don't get it. Yeah, this made more sense when I had added more. So, essentially, when I was looking at the nines table, all of these patterns emerged. It was like in the ones place, always, in every single column, no matter what the multiplier is, the ones place always goes from 9 down to 0, like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Great. Then I was like, the tens place sort of rotates. Like we start with 0 here and we go down 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go 9, like we start with 9, which is we take that last number, put it up, and then keep going, rotating, because after 9 comes 0. So we go 9, 0, 1, 2, 3, 4, 5, 6, 7, 8. You could take the 8 up here, you take 8, 9, comes 0 again, and you keep going. And then the hundreds place would like increase every single time we move down a row. And like all of this is just like 9 times table essentially, because 9 times 1 is 9, 9 times 2 is 18, 9 times 12 is 108, 9 times 22 is 198. So I was like seeing all these patterns like both diagonally, like, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and like horizontally and vertically, and I thought it was really cool, and I wanted to replicate it on another number system. So I guess I'm just going to keep going with these shapes. So like, let's just pretend we have another number after 9 in the ones place. So let's say we have 2 of them. I don't know, the triangle thingy and the partial square thingy. And we're going to pretend that 9 plus 1 in this case is equal to this shape, or this number. Let's call it A. And let's say this A plus 1 is equal to this, which let's just call it B. I don't know why I don't just write A and B. Doesn't matter. Okay. So then we follow this pattern. So we start with the last number that we have in the digits place, which in the 9 number, with like our regular number system is 9. Here it's B. So BA 987 6 5 4 3 2 1 0. And then we do the opposite over here in the tens place, which is 0 1 2 3 4 5 6 7 8 9 A B. And so here we have 2 of the last number, so it's 99. So here it's B and here it's B. And then we keep this last digit the same in every row. So this row is going to have just 9, and this row is going to have just B as its ones place, and this one's going to have just A, and this one's going to have just 9. So we can keep going in this fashion, and I guess I'm just going to try to write it out. So the next one over here, so we've started with the 2, so we get to the 2, and then we get to the 9, because that's the next one, and we keep this B. So then we have BA 9 8 7 6 5 4 3 2 1 0. And this is still like the multiplication table, because this whatever last number is, because like 1 times B is B, and 2 times B is 18, and 3 times B is 29, and 4 times B is 38, and 5 times B is 47, and 6 times B is 56. So that's where we're at right now. Okay? This is, I'll admit, the main thing that this is really showing me is that we do get to choose what we define, essentially. Oh, okay, let me keep going. So this, and then we have this, and this, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, and then we have the number 2 until we have the number 1, we have the 1 in the hundredths place here. So we have the 2. So then this one, I believe, is where we would start the 3. It would be 1 row down. So then by this magical whatever, so here we have like 1, 2, 3, 4, 5. So then we move 1, this is 15. and this is 25. So 25 times b is equal to 227. Who cares? I don't know. But what does this mean? What does this mean? So we can keep adding to the pattern where we skip this number. This has a 55, this has a 44. Oh, in this number system with the 9, we have a total of 10 digits. So it's even. And here in this number system where I added 2 numbers, technically a total of 12 numbers as digits, it's also even. And that must be why in this very first multiplication table, the symmetry is exactly split up in half. So like we have 5 and then on the top and we have 5 on the bottom for like this symmetry. And here we have 6 on the top and 6 on the bottom. So then if it was an odd number of digits as the total, like 11 or something, then it would probably start first this way, where one of the numbers would be like in the void, more or less. It would like be its own mirror, and then the next digits, or in the ones place and the tens place, then they begin to mirror after that, like the 46 and the 64 and the 37 and the 73. And I was thinking about this, and I'm like, this can more or less be generalized, right? Like, I can find the pattern and I can make n the total number of digits there are in the ones place. This is very similar to modular arithmetic, but I feel like it's slightly different, because in modular arithmetic, oh no, we don't. In modular arithmetic, we don't continue going up past the number of digits that we count as the base. So like if we make a base of 3, then all the numbers essentially equal 0 or 1 or 2 or 3. I forgot a little bit how that works. But the point is, we retain our number system when we do modular arithmetic. Here, I'm doing something similar, but I'm not retaining our number system. I'm changing it each time. So I guess anyone out there listening, anyone who knows more than me about math, what am I doing? Is this something that people have done before? I mean, I'm sure someone has, but is there a name for this? Because in my head, I'm like, okay, so let's make n the number of digits in my imaginary number system. I was like, I think I can probably prove this pattern of symmetry exists no matter what n we create our number system out of, and that I realized over here that it probably differs between even and odd. And then I was looking at this. I was like, n over 2, and then n over 2 plus 1 is over here for this column, and this is like where the symmetry happens, which row it happens in. But then I'm like, this is slightly dependent on how I've written out the numbers, how I've written out the columns and the rows. Oh, that's what I was writing over here. Yeah, like this is when I write it in columns. Like, what if I didn't? What if I wrote it continuously, more or less, like put this under here and this under here, and so on. Then I was like, then it's not perfectly mirrored. What did I write over here? There are n numbers that have a tens place, but have been displaced by 1. So like, okay, point is, I think it would be possibly cool to write up some sort of formula or proof of something, either of the symmetries. I'm particularly interested in the symmetries right now because I was starting to read the book Love and Math by Edward Frankel, I believe. And he uses symmetry as an introduction into groups, which I learned about in abstract algebra, but we never used symmetry as the introduction. And when he explained symmetry as an introduction to groups, suddenly it all made sense to me, and groups made sense to me. And like the extension that we can have groups even if it's not based on symmetry, all of it started to make sense to me. And I was like, whoa, like symmetry is actually a base of so many things. Like if we really think about it, where was I drawing this? That symmetry is the basis of geometry, right? Because we have different transformations that happen, whether it's translation, reflection, rotation, and it's like which of these combinations maintain their symmetry, and then that clearly like also applies to groups, which in itself is like all connected to set theory, which I remember learning about in proofs class. Like, you know, symmetry of different sets, whether a set is closed or not, and like different number systems. And then that also connects to modular arithmetic, because isn't modular arithmetic in itself like the circle? It's like the symmetry that we're defining of the numbers. Anyway, my point with that was that I think it's really cool that a lot of things seem to connect to symmetry in math, and I'm feeling like that's something I didn't understand before and would like to explore more, because it probably holds some information or insights that I haven't realized yet. And my other point is that all of these things are connected in these different classes that I took between abstract algebra, geometry, cryptology, and proofs class. And I'm like, I'm thinking about all of these concepts right now together. And this is where I'm really glad that I'm doing this not in a class, because otherwise they would somewhat be separated between the classes. And right now I get to think about all these things together. And I'm learning about braid groups, which might actually relate to my thesis project that I did, but I never actually learned about braid groups in college, in my university classes. But it's starting to make sense. So if I understand something of that, or keep learning about that, I'll write it. But one of the coolest things that I'm learning from this book, or that I feel inspired by, is this quote, that one of Gallifan's skills was his ability to rephrase questions asked by others in such a way that the answer became obvious. And Frankel gives this example where if you ask, some drunk guy, like, what is bigger, 2 divided by 3 or 3 divided by 5? He's not going to know. But you tell him, what's better, 2 bottles of vodka for 3 people or 3 bottles of vodka for 5 people, and he'll right away know the answer. And so how do you get that? How do you get that ability to rephrase questions in such a way that the answer is obvious? I'd like to know. I would like to know.